In previous videos, we have looked at the different probability rules such as multiplying rules, addition rules, and the conditional probability rules. We have also looked at counting rules. Those include the fundamental counting rule, the permutations, combinations, and factorials. In this video, what we're going to do is we're going to look at how we can combine the counting rules with probability rules. Meaning, we want to know the probability of an outcome given that there are multiple different combinations of something happening. Now recall that combinations can be written as in choose R, and recall that combinations are things that order does not matter, such as being selected for a committee, things of that nature, where order does not matter. Okay? I'm choosing things out of a bag all at the same time. The formula for combinations is n factorial divided by n minus r factorial times r factorial. Now then, also recall you can use the formula, or if you're using the TI-30 calculators, there is a PRB button in which you can find the permutation and combinations on that will help you with those. When we're looking at probabilities where there are multiple combinations or multiple possibilities, we want to look at it as finding the probability of an outcome is equal to, on the bottom it is going to be the total number of combinations possible. This means doesn't matter color, size, weight, whatever we're looking at, just everything grouped together and how many we're choosing out of that whole group. Okay? On the numerator, we're going to look at how the group is divided up. Meaning, are we looking at men and women? Are we looking at colors? And how many of each item are we choosing? How many men are we choosing? How many women are we choosing? So we're going to look at the possible combinations for group 1 times the possible combinations, and that, let me come down here, possible for group 2, and if we wanted group 3, however many groups we have, I can keep on going, group 4, group 5. Anytime that there's more than one group, I'm looking at how many possible combinations, and I'm going to multiply those for the numerator. Just like we've done previously when we looked at the number of sopranos versus altos, and so forth, we could see the total number of combinations we had. Now we're looking at the probability of those happening when we have multiple items. We want to also divide that by the total combinations for the entire group. Let's look at what this looks like in an example. So here I have an example that says a package contains 12 resistors, 3 of which are defective. If 4 are selected at random, find the probability of getting 0 defective resistors. So let's first write down information that we know. We know that there are a total of 12. Then we have defective, and we have non-defective resistors. Because if they're in this group, they're either defective or they're non-defective. We have 3 that are defective. If we have a total of 12, 3 of them are defective. If I take 12 minus 3, that leaves me with 9 that are non-defective. The resistors have to fall in one or the other of the groups. Notice that these two add up to my total number over here. Okay, so I have 3 in one group and 9 in the other group. So I'm looking at the probability of getting 0 defective resistors. So the probability of 0 defective is equal to, if I want 0 defective, that means I'm going to have, out of the defective group, I have 3, and I'm going to choose 0 of them because I don't want any of them to be defective, times the non-defective. I have 9 to choose from. Remember that I'm selecting 4 altogether. So if I chose 0 from the first group down here, I have to choose all 4 of them from the non-defective group. These two numbers here of the choosing, my R's here, must add up to my total that I'm choosing. So let me write that there. I'm going to choose 4. Okay? That's my numerator. My denominator is how many total I have. So I have a total of 12, and I'm going to choose a total of 4. Then I can do the actual calculations. Well, 3 choose 0 is 1. There's only one way I can choose 0 of them. 9 choose 4. You can either do it out by hand or you can use your calculator, either way. That is going to be 126. 12 choose 4 is going to be 495. So I have 1 times 126, which is going to be 126 divided by 495. When I do that division, that is going to give me 0.255. Therefore, the probability of getting 0 defective resistors when selecting 4 is 0.255. So again, I have on the numerator, I have the total number of combinations. I can start with 3 defective and choose 0 of them, times the total number of combinations. I have 9 non-defective and choose 4 of them. On my denominator, I have a total of 12 resistors in the package, and I'm going to choose 4 of them. Let's continue on using the same type of example. 12 resistors, 3 are defective. This time I want to get 1 that is defective. So again, I have a total of 12. I'm going to choose a total of 4. I have 3 that are defective. I'm going to choose one that is defective. I had 9 that are non-defective. Now if I'm going to choose a total of 4, and I've already chosen 1 from the defective group, how many does that leave me to choose from the non-defective group? That's going to be 4 minus 1, which will give me 3 that I'm going to choose. Again, notice that 3 plus 9 gives me my total of 12, and 1 plus 3 gives me my total of 4. So it's a real good idea if you write things down kind of in this format where you have your totals over here and then you have your groups. That way you can kind of add across here the 9 plus 3, that gives you your total, 3 plus 1, that gives you your total that you're going to choose. Then when we write out our formula, probability of 1 being defective, I'm going to start with my defectives. I have 3 to choose from, and I'm going to choose 1. Times my non-defectives, I have 9, and I'm going to choose 3. Now on my denominator, I have a total of 12, and I'm going to choose a total of 4. Again, notice that my first numbers, 9 plus 3, add up to 12, and my last numbers, 1 plus 3, add up to 4. Very important. Doing our calculations, 3 choose 1. There's 3 different ways of doing that. 9 choose 3 comes out to be 84. And we've already done the 12 choose 4, which is 495. So 384 is equal to 252 divided by 495, which is going to give me 0.5. Let's do that again. 0.509, and that's must be holding it at a different angle. 509. So the probability of getting one defective resistor when 4 are chosen is 0.509. Okay, and remember that we want to make sure that since this is a word problem, just to aim that 0.509, that doesn't answer my question. I need complete sentences. You need to make sure that you relate it back to the original problem. Okay, one more using the same problem. This time we're going to get 3 defective resistors. So again, we have a total of 12, and we're going to choose 4. We had 3 defective and 9 non-defective. This time we're going to choose 3 from the defective because we want 3 defective. 4 minus 3 gives me 1 that we're going to choose from the non-defective. Again, I have to make sure that my numbers add up to my totals over here. So the probability that 3 are defective is equal to, for my defectives, I have 3 to choose from, and I'm going to choose 3 of them. times my non-defectives. I have 9, and I'm going to choose 1. Then my totals. I have 12, and I'm going to choose 4. 3, choosing 3. There's only one way I can do that. 9, choose 1. There are 9 different ways I can do that. 12, choose 4. We've already done that, which is 495. So I get 9 divided by 495, which is 0.018. The probability of getting 3 defective when 4 are selected is 0.018. Again, I'm relating the number that I found back to my original problem. Okay? Again, make sure that you're dividing things up into their groups. Make sure that your numbers add up to your totals. How many were in each group have to add up to your total that are in, and also how many that you're choosing from each group have to add up to the total number that you're choosing. Okay? Practice these, and if you have questions, please feel free to ask me.